is certainly an established fact that nature has behaved largely uniformly up to now, but we cannot appeal to this fact to argue that nature will continue to be uniform, because this assumes that what has happened in the past is a reliable guide to what will happen in the future, which is the uniformity of nature assumption. If we try to argue for UN on empirical grounds, we end up reasoning in a circle. The force of Hume's point can be appreciated by imagining how you would go about persuading someone who doesn't trust inductive reasoning that they should. You would probably say, "Look, inductive reasoning has worked pretty well up until now. By using induction, scientists have split the atom, landed men on the moon, invented computers, and so on. Whereas people who haven't used induction have tended to die nasty deaths. They have eaten arsenic, believing that it would nourish them, jumped off tall buildings, believing that they would fly, and so on. Therefore, it will clearly pay you to reason inductively." But of course, this wouldn't convince the doubter, for to argue that induction is trustworthy because it has worked well up to now is to reason in an inductive way. Such an argument would carry no weight with someone who doesn't already trust induction. That is Hume's fundamental point. So the position is this. Hume points out that our inductive inferences rest on the UN assumption, but we cannot prove that UN is true, and we cannot produce empirical evidence for its truth without begging the question. So, our inductive inferences rest on an assumption about the world for which we have no good grounds. Hume concludes that our confidence in induction is just blind faith. It admits of no rational justification whatever. This intriguing argument has exerted a powerful influence on the philosophy of science, and continues to do so today. Popper's unsuccessful attempt to show that scientists need only use deductive inferences was motivated by his belief that Hume had shown the total irrationality of inductive reasoning. The influence of Hume's argument is not hard to understand, for normally we think of science as the very paradigm of rational enquiry. We place great faith in what scientists tell us about the world. Every time we travel by aeroplane, we put our lives in the hands of the scientists who designed the plane. But science relies on induction, and Hume's argument seems to show that induction cannot be rationally justified. If Hume is right, the foundations on which science is built do not look quite as solid as we might have hoped. This puzzling state of affairs is known as Hume's problem of induction. Philosophers have responded to Hume's problem in literally dozens of different ways. This is still an active area of research today. Some people believe the key lies in the concept of probability. This suggestion is quite plausible, for it is natural to think that although the premises of an inductive inference do not guarantee the truth of the conclusion, they do make it quite probable. So even if scientific knowledge cannot be certain, it may nonetheless be highly probable. But this response to Hume's problem generates difficulties of its own, and is by no means universally accepted. We will return to it in due course. Another popular response is to admit that induction cannot be rationally justified, but to argue that this is not really so problematic after all. How might one defend such a position? Some philosophers have argued that induction is so fundamental to how we think and reason that it's not the sort of thing that could be justified. Peter Strawson, an influential contemporary philosopher, defended this view with the following analogy. If someone worried about whether a particular action was legal, they could consult the law books and compare the action with what the law books say. But suppose someone worried about whether the law itself was legal. This is an odd worry indeed, for the law is the standard against which the legality of other things is judged, and it makes little sense to inquire whether the standard itself is legal. The same applies to induction, Strawson argued. Induction is one of the standards we use to decide whether claims about the world are justified. For example, We use induction to judge whether a pharmaceutical company's claim about the amazing benefits of its new drug are justified. So it makes little sense to ask whether induction itself is justified. Has Strawson really succeeded in diffusing Hume's problem? Some philosophers say yes, others say no. But most people agree that it is very hard to see how there could be a satisfactory justification of induction. Frank Ramsey, a Cambridge philosopher from the 1920s, said that to ask for a justification of induction was to cry for the moon. Whether this is something that should worry us or shake our faith in science is a difficult question that you should ponder for yourself. Inference to the best explanation. The inductive inferences we've examined so far have all had essentially the same structure. In each case, the premise of the inference has had the form, all x's examined so far have been y, and the conclusion has had the form, the next x to be examined will be y, or sometimes, all x's are y. In other words, these inferences take us from examined to unexamined instances of a given kind. Such inferences are widely used in everyday life and in science, as we have seen. However, there is another common type of non-deductive inference that doesn't fit this simple pattern. Consider the following example. The cheese in the larder has disappeared, apart from a few crumbs. Scratching noises were heard coming from the larder last night. Therefore, the cheese was eaten by a mouse. It is obvious that this inference is non-deductive. The premises do not entail the conclusion. For the cheese could have been stolen by the maid, who cleverly left a few crumbs to make it look like the handiwork of a mouse. And the scratching noises could have been caused in any number of ways. Perhaps they were due to the boiler overheating. Nonetheless, the inference is clearly a reasonable one, for the hypothesis that a mouse ate the cheese seems to provide a better explanation of the data than do the various alternative explanations. After all, maids do not normally steal cheese, and modern boilers do not tend to overheat. Whereas mice do normally eat cheese when they get the chance, and do tend to make scratching sounds. So although we cannot be certain that the mouse hypothesis is true, on balance it looks quite plausible. It is the best way of accounting for the available data. Reasoning of this sort is known as inference to the best explanation, for obvious reasons, or IBE for short. Certain terminological confusions surround the relation between IBE and induction. Some philosophers describe IBE as a type of inductive inference. In effect, they use inductive inference to mean any inference which is not deductive. Others contrast IBE with inductive inference, as we have done above. On this way of cutting the pie, inductive inference is reserved for inferences from examined to unexamined instances of a given kind, of the sort we examined earlier. IBE and inductive inference are then two different types of non-deductive inference. Nothing hangs on which choice of terminology we favor, so long as we stick to it consistently. Scientists frequently use IBE. For example, Darwin argued for his theory of evolution by calling attention to various facts about the living world, which are hard to explain if we assume that current species have been separately created, but which make perfect sense if current species have descended from common ancestors, as his theory held. For example, there are close anatomical similarities between the legs of horses and zebras. How do we explain this if God created horses and zebras separately? Presumably, he could have made their legs as different as he pleased. But if horses and zebras have both descended from a recent common ancestor, this provides an obvious explanation of their anatomical similarity. Darwin argued that the ability of his theory to explain facts of this sort, and of many other sorts too, constituted strong evidence for its truth. Another example of IBE is Einstein's famous work on Brownian motion. Brownian motion refers to the chaotic zigzag motion of microscopic particles suspended in a liquid or gas. It was discovered in 1827 by the Scottish botanist Robert Brown, 1773 to 1858, while examining pollen grains floating in water. A number of attempted explanations of Brownian motion were advanced in the 19th century. One theory attributed the motion to electrical attraction between particles, another to agitation from external surroundings, and another to convection currents in the fluid. The correct explanation is based on the kinetic theory of matter, which says that liquids and gases are made up of atoms or molecules in motion. The suspended particles collide with the surrounding molecules, causing the erratic, random movements that Brown first observed. This theory was first proposed in the late 19th century, but was not widely accepted, not least because many scientists didn't believe that atoms and molecules were real physical entities. But in 1905, Einstein provided an ingenious mathematical treatment of Brownian motion, making a number of precise, quantitative predictions which were later confirmed experimentally. After Einstein's work, the kinetic theory was quickly agreed to provide a far better explanation of Brownian motion than any of the alternatives, and skepticism about the existence of atoms and molecules rapidly subsided. One interesting question is whether IBE, or ordinary induction, is a more fundamental pattern of inference. The philosopher Gilbert Harman has argued that IBE is more fundamental. According to this view, whenever we make an ordinary inductive inference, such as, all pieces of metal examined so far conduct electricity, therefore all pieces of metal conduct electricity, we are implicitly appealing to explanatory considerations. We assume that the correct explanation for why the pieces of metal in our sample conducted electricity, whatever it is, entails that all pieces of metal will conduct electricity. That is why we make the inductive inference. But if we believed, for example, that the explanation for why the pieces of metal in our sample conducted electricity was that a laboratory technician had tinkered with them, we would not infer that all pieces of metal conduct electricity. Proponents of this view do not say there is no difference between IBE and ordinary induction. There clearly is. Rather, they think that ordinary induction is ultimately dependent on IBE. However, other philosophers argue that this gets things backwards. IBE is itself parasitic on ordinary induction, they say. To see the grounds for this view, think back to the cheese in the larder example above. Why do we regard the mouse hypothesis as a better explanation of the data than the maid hypothesis? Presumably because we know that maids do not normally steal cheese, whereas mice do. But this is knowledge that we have gained through ordinary inductive reasoning, based on our previous observations of the behavior of mice and maids. So according to this view, when we try to decide which of a group of competing hypotheses provides the best explanation of our data, we invariably appeal to knowledge that has been gained through ordinary induction. Thus, it is incorrect to regard IBE as a more fundamental mode of inference.